Okay, guess what? More models. Build beta-D-glucopyranose.
Run.
Did you build it? Should look like that. Now, I know that's hard to see from far away, that's why you want your own. How do I know it matches? Look at the two ways that we have drawn this six-membered ring. You need the model to understand those two ways. We are very comfortable, and by far, I agree, the easiest way is to draw it with this representation, where the bonds look flat, where they look like they're in the plane, the ring bonds, which means that we draw that. And then we draw everything as dashes and wedges as opposed to axial equatorial. So let's take a look at that. If you have that, how would you know which one you have? If you built this model, if your eyeball was going straight down the middle, even though it's zigzag on the side, which is what makes it a chair, if you look straight down the middle, suddenly those bonds look planar. And that's what this representation is. It's when your eye is going straight down that chair, you get what the representation you're really used to. So if I draw this out, it would have my, let's see, yeah, up, down, down. And then I have a CH2OH up. Heard a hawk. Nature is out today. Sorry, that's why. There it is. I hope the quail are okay. Okay. So, back to our chair, our ring. So our Pyranos ring, we're used to that. What you want to be, the language you want to be using when transferring from each of these is not getting trapped into the whole axial equatorial sort of definition, but up and down. Up versus down is what matters. So in other words, in this representation, the wedge is up, the dash is down, right? The Haworth projection, I think you're going to like more than a chair. It's usually more straightforward. So what's the difference between the flat and the Haworth? So if you take your model, look at it straight so that you can see down that middle, like right here. Look at it straight down so you can see that center point. Now take that model and then orient it so it matches what's on the paper. So we have that oxygen in the upper right-hand corner. We have the hexagon ring lying on its side, not a point, not a vertex. Like a frost diagram, you might be used to drawing them on a point. We want them on the side. And then we want the OH at the top here. All right, so orient it like that. So you're looking straight down. Now turn it perpendicular. That's the chair, right? Where we're looking at it from the side. So that's the chair. Now turn the chair back towards you as you bring the O back. Okay, so we have this flat side here. And so before it looks like they're all on the same plane again, just before that, you can tilt it back just a little away from you so that the front is coming toward you and the back is going away. So that's why these are bolded a little more. That is the Haworth projection. Notice you suddenly get to draw up and down bonds instead of axial and equatorial, which it really, sometimes they look axial or axiatorial because it's hard sometimes to get those bonds just parallel. It's not, you might be able to visualize it. So, in other words, this H parallel to this bond. Without a ruler, that's hard to get it looking right, and it takes a lot of practice. You don't have to worry about that here. No slanting. The Haworth projection, which is this one, allows you to take your beloved planar cyclohexagon and just tilt it slightly towards you so that this bottom part is coming toward you, right? It's a smile because you're happy to draw it that way. If we drew in all of the bonds, the H's, they would just be straight down or straight up wherever there was an open spot. So that oxygen is up. That means the H is down. And likewise, we don't want to miss that one. So once again, to know you did that right, look at our reference oxygen. The one just to the right of it has an up OH. And then the next one is down, and so on. Up, down, and then we have our CH2OH. And then we see that they are beta. And then finally, the last way we'll represent the ring is, of course, the chair. Both of these are very popular. I see these in literature all the time. The chair is very well established and a good way to represent what's going on in 3D space. It's probably the best way, actually, because we know they're not straight up and down bonds. But the fastest way to draw it is certainly a Haworth. So you want to, and so there's a lot of publications that will have Haworth projections as well as the biochem textbooks. So you want to be comfortable with all three, okay, so that you can visualize what's going on. You also want to be comfortable, just like we practice closing the ring to get to it, you want to be comfortable, remember that's reversible, going back and opening it and seeing where it came from, what straight chain did it come from. So that means interconverting between Fisher, straight bond line, regular bond line ring, Haworth, and chair. Lots to practice there. Okay, so how about we draw the Haworth projection of something that's about to close into a ring. So here's D mannose. Can we draw the Haworth projection after it closes into a ring? So in other words, one rule for the Haworth projection is we're always going to draw that oxygen in the upper right-hand corner. Has to be there. Now you might see where it's not, but this is what we're going to do just to keep it consistent. And so most resources will follow this rule. So we're going to keep it upper right-hand corner. Okay, so then we fill in everything else. That means we're going to have to know how to fill in these empty bonds. And then this one will have our CH2OH somewhere and our OH. Since we know it's beta, this one we already know has to look like this, so that the OH and it's D, that means it's going to actually be up. So we just kind of derived that actually. So the D pyranoses always have the CH2OH, if you have a beta, always has the anomeric OH up. So I have that as a rule here so that we don't forget. So always draw your hexagon with the oxygen atom in the upper right-hand corner. I guess I can highlight, that's okay. Draw your CH2OH group in the upper left-hand corner. If the aldohexose is D, they are up. It is up. Here we go, D. If it is D, that CH2OH will be up. What did I mean by that? That means right here, the CH2OH must be up if it's D. So let's write that rule down here as well. D sugar, therefore CH2OH is up. You don't have to memorize that. You'll get that by accident. We're actually going to work it out here and prove that it is up. Also, anomeric alcohol is on the other side of the CH2OH carbon. And the alpha beta helps you determine where to put it. Okay, so let's go back to alpha beta. We were told D helped us figure that out, right? We also can see that it's D here. And then beta means that these have to be cis, which means the OH must be up on the anomeric carbon. That actually wipes out 2 of the 5 you have to draw properly. Now, how to place the other 2, up or down OHs. So I think it's best to visualize them, and then we'll kind of come up with a pattern after that. So let's derive it all. In fact, I'm not even a huge fan that I told you these little tricks first, because we need to work through it so that it's not just strict memorization. But I think it's nice to point it out so we watch out for them. So here's the easiest way, I think, to get it together. Now, thinking about the fact that our OH is that's attacking the nucleophile is this guy. That was our nucleophile. This was our electrophile. Okay, so our nucleophile attacked our electrophile. That is not the same orientation as this. So this is our electrophile. And then if we number our carbons, 1, 2, 3, 4, 5. Okay, let's do that here. 1, 2, 3, 4, 5. Now in carbon 5, we have the CH2OH, but that's this guy. So we're not going to go 6, 7 because we don't make a 6-numbered ring. So remember, the nucleophile actually comes out over here. It's that B alcohol. So here's our nucleophile to form the hemiacetal. Now, in forming the hemiacetal, we have to do some sort of 3D brain visualization. I want this to kind of at least line up. So where does the hemiacetal get its groups from? That means if it's a hemiacetal, it used to be an aldehyde. And we can see that with the number. It's carbon 1. So that was our electrophile. This was our nucleophile. Okay, so I'm going to break this into steps. Step 1. And I'm going to have you try some of this. I'll pause. Lay down fissure. Then rotate C5 to put oxygen 6 in place. That's going to be step 2. I didn't do any rotating. Let's rotate. The easiest way to rotate is to draw the ring shape. Have it almost there. I don't like that. I'm going to break this into more steps. Okay. Let's break this into steps. Step 1. Easy. Lay down your fissure. It's going to fall like timber. Okay. So lay down fissure. I'm putting my aldehyde fall down to my right because my hemiacetal used to be an aldehyde. That's where it's on my right. So I want to match the end. Aldehyde on right. Okay. Now, number 2. Rotate to ring shape. So we're going to line it up so it starts to look more like a ring. So in other words, it's not going to be closed yet because we have to work out how it closes. But we'll do, we could do this much. So it's not closed yet. So there's my aldehyde carbon. And then we can put our fissure pieces in. So all I did was kind of bend it. It's still going to have the same orientation of everything. So there's my tail. So I just took the tail and I bent it around to match the head. So that's not hard brain work because the ups from before are the ups after. And the downs, likewise with the downs. Now, time to close the ring. Uh-oh. Notice that this is not going to attack. This is what attacks. That's my nucleophile. It's going to have to rotate to attack here. So it needs to be in place. So let's rotate it to put it in place. So in other words, I'm redrawing this ring. So number 3. Redraw ring with C5 rotated to put the needed OH in place. Okay. other words, everything is the same. So see 1, 2, 3, 4, 5. 5 is the ones that's changing. So let's keep 2, 3, and 4 the same. 2 is OH up, 3 is OH up, 4 is OH down. Don't touch 5 yet, that one changed. Okay, so what I'm doing is putting this in place, this OH that needs to attack. Now what I want you to do is work that out. When you did that rotation, who goes up here and who goes down here? So stop, drop, do that rotation, use a model if you have to, and come back to check. When you check, I'm going to erase this so that we have a spot to write it. Okay, did you rotate? I hope you saw that when we did that rotation, our OH, CH2OH, oops, not water, CH2OH is at the top, and our H is at the bottom in order for this to be into place. And then this can attack and make that anomeric carbon as it closes the ring. So that goes and becomes this one. Now, once again, anomeric carbon means that this is mutarotatory. It could go either way. And we have OH up, H, H, OH down, H, and there we go. Okay, so that's beta-D-mannopyranose. Now, what do we know about mannopyranose and D? Those are those rules we came up with. We kind of proved it structurally here. If it's D, the CH2OH is up. Because, why is that a rule? That's because that is the carbon that determines whether it's D or L. So when it's not in a ring, the CH2OH is hanging down, and we kind of ignore it, but the OH is the one that's on the right, and that makes it D. But now that the OH is part of the ring, we have to determine the placement of the CH2OH in something that's D versus L. If it's D, it's up, L, it's down. So just for practice, draw, now that we know what this looks like, draw alpha L mannopyranose. And check back. What does that look like? So you'll start with everything started to draw out, but then you have to decide where it all goes. Okay, fill it in and check back, okay? Okay, so you're back. L means our CH2OH is down. Alpha means our CH2OH is trans to anomeric OH. The rest is the same. So these are not the anomeric or the CH2OH groups, so they have to be like this. It's the rest, those last two that'll be different. L means our CH2OH is down. So there's our L. This needs to touch that bond. There we go, or that atom. Alpha means trans. So since the CH2OH is down, we must have the anomeric OH up. And voila. So it's really helpful to establish a point of reference. If you have one, you could draw lots of other isomers from it. Okay, so those rules are once again summarized here. And one more rule I'll add here. Oh, it's actually there. It got chopped off. So you're not done with the rules. Look how this one continues here. draw their alcohols. So that took a long time. I mean, phew. Can we use this long problem-solving process to make it a little faster for us in the future? Yes. And it's not a trick because you worked it out. And if you do this a couple more times, you will connect it to the pattern. And then to someone else who doesn't know how to do it, it'll look like a trick, but it's not because you have a pattern established. So that's when it's okay to use these sorts of rules. But notice the step I had to do to derive all this. I had to lay it down on its side. Notice everything that was on the left ended up, everything that was on the right ended up down. Okay, so then I'm going to close the ring. So if I were to just draw my ring straight from here, which we can do that in just a second, we're going to say, actually I have the template right there. I'd say, well, the consequence of that first step, which I don't need to redraw to figure this out, everything that is on the fissure, if it's on the left, it's up. If it's on the right, it's down. So let's do this faster now. Let's take advantage of the space. This will be the equivalent of our speed run for drawing, converting a fissure to I gotta go back to the original structure because it's on that page. Converting a fissure to a Haworth. So it was a CH2OH down here with 4 stereocenters. 1, 2, 3, 4. Left, left, right, right. H, 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 H. Okay. Let's combine these rules. Step 1, draw the hexagon with the O in the upper right-hand corner. This is the speed run version. We're going to draw O. There we go. Step 2, draw the CH2OH in the upper left-hand corner. Draw it up if the aldohexose is D. This was, in fact, D-mannose. So up CH2OH. We've got to determine the rest. Here's our anomeric carbon. Use alpha beta. Well, we were asked to draw beta. So beta D mannopyranose was the goal. Now that we know that it has to be beta, so I've taken care of the fact that it's D, that means the CH2H is up. Taking care of the fact that it's beta means that since the CH2H is up, the OH must be up on the anomeric carbon. The rest that makes it mannopyranose come from these 3 carbons here. We get that from the fissure. Left means up, right means down. So work it around. So carbonyl carbon. Next carbon over has an OH left. So that's up. Likewise up. Right means down. OH. Okay. And we're done. So you can do that, but it makes more sense if you work through it. So do work through it too. Like anything else, right? Okay, this is worthy of a break. When we come back, we're going to talk about 5-membered rings, what they look like when they close, because they have a big role biologically speaking as well. Go build models and do some problems with 6-membered rings, and we'll do the 5-membered rings. See you soon.